Okay, so I've got to remember I've literally shackled myself to the computer now. So for section 2.3, when we're dealing with the limit laws, we would like to be able to just substitute the number that the variable is approaching into our function, but we can only do that under certain cases. Specifically if the function is what we call continuous, but we'll get to the formal definition of continuity in a later section. So for a problem like this, we would start out maybe by trying direct substitution and seeing if that works. But anytime you have a rational expression, you can't divide by 0. And in this case, my denominator is only h. So if h approaches 0, I can't substitute in. If h were approaching any other number, that'd be great, but not as h approaches 0. So direct substitution fails. We have to try something else. Now, the trick that we did on the last problem of factoring the numerator and denominator, that doesn't work because the numerator is a radical expression, and those don't factor like polynomial expressions do. So we're going to have to try something else. And what we're about to do, you may have done in the case of denominators, but in this case, we're going to be doing what's called rationalizing the numerator. Because if you take a rational expression, now what I'm about to write, I'm going to erase, but I just want to show you that if you take any rational expression, let's say, I don't even want to use h because I don't even want to relate it directly to the variable that's in this problem. But if I had something like this, square root of x plus 1. If you take square root of x plus 1 and multiply it by square root of x minus 1, now these two numbers in parentheses, the square root of x plus 1 and square root of x minus 1, these are what are called radical conjugates of each other. Because, well, I guess technically it's not true because the radical part is what would need to change sign. But in this case, if you were to multiply these two expressions together, look what happens if you just use FOIL. What is square root of x times square root of x? What's that equal to? X. The outside terms is x times negative 1, which is, square root of x times negative 1, which is negative square root of x. The inside terms is going to be positive square root of x. And the outside term, the last terms give you plus 1 times negative 1, which is negative 1. But what happens to those two middle terms? They cancel out. So you're left with an expression that doesn't have a radical in it. This is exactly what we want to do to that numerator. So what I'm going to do is I'm going to take this sign right here. If I were to multiply the numerator and denominator by the square root of h plus 1 plus 1, then when I multiply the numerators out, this same little trick is going to work, and I'm going to end up with an expression that has no radical in it. Now the radical is going to move into the denominator. That's okay. Watch what happens when we get there. So let me just back out of this. So I want to go to this screen. So this process of multiplying by a radical expression so that the product has no radical in it is what we call rationalizing the numerator. Usually we do this to the denominator because it's easier to take a number like square root of 2 and divide it by 2 than it is to take a whole number and divide it by a radical. It's just our brains don't naturally work like that. It's a little harder to do. But if I multiply, why did I multiply it by the numerator and denominator? Yeah, because this red fraction right there, that's just equal to 1. So I haven't changed what I'm taking the limit of. I am just rewriting it in a more convenient way so that I can apply some of the rules that we've already talked about. Okay, so let's multiply out that numerator. So multiplying out that numerator is going to, well, I can do the work off to the side here. So we have square root of, oops, that's what I want. Square root of h plus 1 minus 1 times square root of h plus 1 plus 1. Notice I didn't change the sign that was under the radical. I only changed the sign between the radical part and the rational part of that numerator. So if I multiply these two together, I'm going to have this square root of h plus 1 times square root of h plus 1. So that's this h plus 1 that's right here. Now, if you proceed with FOIL, the outside and the inside terms are going to cancel each other out because they're the same expression just with opposite signs. And the last term is going to have this negative 1 times this positive 1, which will give us the negative 1 here. Great. So now our numerator has no radical in it, but our denominator does now. So it doesn't look like I've changed much, but now that I look at the new numerator, can I simplify it at all?
Yes, you can subtract the 1.
The plus 1 and the minus 1. Get rid of them. So once that plus 1 and the negative 1 subtract out, the numerator only has an h in it, which is perfect because my denominator has a factor of h that it will cancel with. So now that I have freed that factor of h up in the numerator, I can take it one step further and divide out that common factor of h. Now if we go back, well, I don't have to go back, it's already on the screen. If I look back at the original problem, h being in the denominator, that was the problem because I can't let h be 0. But I have gotten rid of the one number in the denominator that was causing the problem. So if that number is gone now, direct substitution works. So I can plug 0 in now for h. And when I simplify this, I get that the limit is equal to a half. But I couldn't do direct substitution right from the start because the limit law involving quotients, remember there was a condition that the limit of the function in the denominator could not be equal to 0. It was in this case. So that limit law does not apply to this to the problem as it was originally written. So in some problems, direct substitution applies directly. In some problems, especially if they're rational functions, then maybe factoring or either rationalizing the numerator or rationalizing the denominator. It doesn't matter which one you rationalize. So, but the idea is to hopefully simplify it down into an expression where direct substitution does apply. And then I can just take it from there and plug the number in. Unfortunately, you're going to have some functions that seem to not work in any of those other tricks don't seem to work on it. It doesn't rationalize, it doesn't factor, and direct substitution still doesn't work. Some functions are just hard. So we have some ways to get around that sometimes. Okay. Now, this is a particular limit that we're going to see this kind of limit later in like section 2.8. But for now, let's just see if we can't go about figuring out how to work this problem. Can I do direct substitution? No. With that h in the denominator, I can't do it. Now the numerator, there's not a common factor of h, so I can't just divide it out right from the start. But my goal is, hopefully, I can rewrite that expression so that somewhere later in the problem, the numerator has a free factor of h floating around somewhere, and as soon as that's the case, it will cancel with that factor in the denominator, And once that is gone, direct substitution is open to me now. But I got to get there first. So I've got to multiply out what that numerator is. So I've got to take what is, have I done the work on the next screen? I have. I couldn't remember if I put this slide in or not. So this x plus h, this work over here in red, this is just to show the work of what this part of the expression is going to simplify to. So anytime you have a polynomial, or in this case a binomial that's raised to a power, you can't just raise the individual terms to powers. You have to multiply x plus h times x plus h times x plus h, and go through the process of multiplying that out using FOIL. So when I do that, and I'll let you verify this outside of class, but that x plus h cubed simplifies or multiplies out to x cubed plus 3x squared h plus 3x h squared plus h cubed. So when I substitute that into the problem, the x plus h cubed contributes all of these red terms that are in this numerator. This negative h cubed, I'm sorry, this negative x cubed is the one that was originally in the problem to start with. Now look at the numerator. Is there anything that simplifies? Yeah. We have a positive x cubed on the left and a negative x cubed on the right. So those subtract out. And if I look at every other term in the numerator, every other term has a factor of h, which I can then factor out of the numerator. As soon as that occurs, I have that common factor with the denominator. And then from this point on, now it is a direct substitution. Well, it's a limit of a polynomial, but it's only h that's approaching 0, not x. That's important to note in this case. So as h approaches 0, what's happening is this term is going to 0, and this term is going to 0. But nothing is happening to this. As far as h is concerned, this 3x squared is constant. So when I do direct substitution, I just plug in 0 for h, and I end up with 3x squared. Now, like I said, this limit, this particular limit of the x plus h cubed minus x cubed over h, this kind of limit is going to come up in section 2.8 or 2.9, somewhere at the end of chapter 2, because this limit is actually what we call the derivative of the x cubed function. And you will see later that the derivative of x cubed should be 3x squared. And we're going to get some rules later on that allow us to get to this conclusion without having to go through this limit all the time. But this is how this particular limit would be worked. Now, you could probably see that if this were x plus h to the 6th, it doesn't change the difficulty of the problem much. All it changes is I would have x plus h times x plus h times x plus h times x plus h times x plus h. And it would just be, it would take longer to multiply out. I could still do it. I got better things to do with my day. So it's unlikely that if I were to ask a problem on a test, this is not unreasonable. X plus h to the 10th, that's a little harder to find unless you know the trick to get around to get this answer quickly. There is a trick for it, but we don't teach it here. Simply because of the fact that I'm not really in the business of teaching shortcuts. But it does work. In any case, before I go on, is there any part of this problem that you have any questions about? And there's really no guarantee from the start of the problem what it's going to take. You just got to try it. Okay, and this first theorem that I've got written at the top of the screen, I already said this last week, that what this first theorem says is the limit on the left, x approaches a of f of x equals L. This one right here, this is the two-sided limit. That the two-sided limit is equal to a number if and only if. So if you ever see IFF, especially in mathematical texts, that means if and only if. It means the direction goes in both directions. So this limit is equal to L if and only if the left-hand limit and the right-hand limit approach the same value L. So this is the left-hand limit, and this is the right-hand limit. If either one of those one-sided limits do not exist, then the two-sided limit won't exist. And if the one-sided limits are not equal to each other, they could both be equal to real numbers, but not equal to the same value. If that's the case, then the two-sided limit won't exist at all. But it's also true that if I tell you that the two-sided limit exists, I am implicitly telling you that the one-sided limits also exist and they approach the same value. That's what it means by the if and only if. I should be able to start from the left-hand side and conclude the right-hand side. I should also be able to start from the right-hand side and conclude what's on the left-hand side. If you see an if-then statement in a mathematical text, this actually applies to logic in general, but if-then, usually you start with the if part, and then the then part is the conclusion. The implication does not necessarily go in the other direction. Like, if I were to say, if today is Tuesday, then today is a weekday. That is a true statement, but it doesn't go in the other direction. If I say, if today is a weekday, then today is Tuesday, that's false now, because there are many other weekdays it could have been. But if and only if statements work in both directions. So, the other theorem, this is the one that's a little more important, because this is going to help us gain some insight on what do we do when we encounter a function that's a little difficult to take a limit of. So our assumptions here is we're starting with a function, two functions, f of x and g of x. And I want, so f of x is in blue and g of x is in red. And in our assumption, f of x is less than or equal to g of x when x is near a, except possibly at a itself. So I've drawn a picture right here that sort of demonstrates the assumptions that we're supposed to be assuming in this particular problem. So in this case, this is the number a right here that we are approaching. Now, notice that f of x is not less than g of x all the time. There are some cases over here where the blue function is on top of the red one. So over here, f of x is greater than g of x. But in our assumption, we're only care about what happens when x is near a. So if I look at some neighborhood around a, ignoring everything else, then I do have that f of x is less than or equal to g of x, except in this case, at a, the blue function jumps up here, and the red function jumps down. So in my picture, f of x is actually greater than g of x at a. But remember, limits don't care what happened at the number you're approaching, only what happens as you get close to it. So as far as the limits are concerned, these individual values don't even need to exist at all. We're only looking at the functions right here as x approaches a. So we want to be able to draw some kind of conclusion about the limits of f and g as you approach a. Well, if f is less than or equal to g of x as you approach a, then what's going to happen is f of x is going to be approaching this value, where g of x is going to be approaching this one. So I can say that I don't know what those numbers are exactly because I don't know what f and g is. But I do know that the limit of f of x has to be less than the limit of g of x, simply by the nature of it being the limit of f of x would be right about here. The limit of g of x would be right about here. And on the y scale, we do have that it is less than or equal to the limit as x approaches a of g of x. Okay. This next theorem, it's got a couple of different names for it. The one I always learned it as was the squeeze theorem. It's the one I'm going to refer to it as. And the squeeze theorem is a natural implication of the theorem that I just explained. Only now, instead of working with two functions, we're working with three functions, f, g, and h. And now we've got it to where f of x is less than g of x, which is less than or equal to h of x. So I've got it drawn here in my picture where f is the smallest function, g of x is the middle function, and h of x is the largest function. Here is the value a that we're approaching. And we have made another assumption in the problem. We've made this assumption right here. Oops. That the limit of f of x, in other words, the limit of the smaller function, and the limit of the larger function, h of x, both approach the same value as x approaches a. So what happens is these functions pinch down to a single point. But g of x is in the middle of them. So if g of x is locked in between those two functions, and the two functions that were bounding it pinched down to a single point, the only place for g of x to go is straight through that same value that f of x and h of x pass through. So if we know what the limit of the larger function is and what the limit of the smaller function is, if those numbers are the same value. Now, if those two numbers exist, the only thing you're going to be able to say about the limit of the middle function is that it's between the upper and the lower boundaries. But if those upper and lower limits are the same number, the limit of the middle function has no wiggle room. It has to go right through that same point. So what this is going to do is this is going to give us a tool to be able to take limits of functions that at first glance appear to be pretty difficult. Like this next one. This next function is going to fail everything we try to throw at it. So in this particular problem, will direct substitution work? Why not?
Because when you plug it in for the x and the sine function, it's going to be
Right, we're taking sine of pi divided by x. So as x approaches 0, you're going to be dividing by 0 in that angle measure. So you can't use direct substitution. Factoring isn't going to help here because if you look back at the problem where we did factoring, we started with a rational function. And we wanted the factors to cancel with something that was in the denominator. There's no denominator here for anything to cancel with. So even if I could get a factorization, the factors are stuck there. I can't get rid of them. Okay, yes, there's a radical here, but rationalization isn't going to help this because there's no plus or minus here. There's nothing I'm really going to be able to multiply it by and simplify the problem to where I could use direct substitution. So we've got to try something else. And what we're going to try is, I would like this function, the one that I'm trying to find the limit of, I would like it to be this middle function right here. If I can find a smaller function and a larger function that bound that other function that we were just looking at, maybe the smaller and the larger function are very easy limits to evaluate. And if I can get lucky, and that those larger and smaller limits approach the same value, I don't have to find the limit of that other function directly. I can just invoke the squeeze theorem and say there's this other function that has no choice other than to take the same value for its limit. So let's try that. So I want to find a smaller function and a larger function. And what do you know about the sine function? What is the smallest of the smallest number sine of x can take on? Y'all remember its graph, right? Starts here. So this is pi over 2, pi, 3 pi over 2, 2 pi. And the function looks like this. So it comes up. Oops, that's garbage. So it comes up, and down, and then back. Yeah, the smallest value it can take is -1. The largest value it can take is +1. So the sine function, regardless of what its angle is, in this case it's pi over x. But we don't care, it's sine of something. Therefore, it's bounded between -1 and 1. So let's get rid of this and make that statement, that -1 is less than sine of pi over x is less than 1. Okay, we get that for free from trigonometry. Now, what I am going to do is multiply all three parts of that inequality by that square root of x cubed plus x squared. If I do that, it looks like this. Now I got one comment I want to make about this. I multiplied a number by all three parts of this inequality, the same value. Why did I not have to change the direction of the inequality? Why am I able to say that this is still less than, and this is still less than right here? Sorry? It's because you only do that if you multiply by a negative value. How do I know that the number I took was positive? How the number I multiplied by was positive. Yeah, this radical right here is a positive radical. If it were negative, if it were intended to be negative, the negative would have been in the problem. But I am multiplying all three parts of that expression by positive square root of x cubed plus x squared. So because I'm multiplying by a positive number, the inequality stays the same. Now, ignore the middle for a second. Look at this smaller function right here. So this is f of x now. This is, the middle function is g of x. This other function is h of x. So look at f of x on the left-hand side. If I were to take the limit as x goes to 0, could I use direct substitution there now? Yeah, because it was the sine of pi over x. That was what was stopping us from using direct substitution in the first place. Now, my smaller function and larger function do not have that pi over x. So direct substitution is valid. So if I do direct substitution for f of x and h of x, what's going to happen is I'm going to get something that looks like this. Well, once we have the inequality set up, the next step is I take the limit of all three of those functions. On the next slide, I actually evaluate what those limits are. So for the smaller limit and the larger limit, direct substitution applies, and both of them are equal to 0. So this limit in the middle, that's the one that I was originally asked in the problem. But it's bigger than or equal to 0, and it's smaller than or equal to 0. And the only way this is going to work is if that limit is actually equal to 0 itself. So we didn't have to find the limit of the original function to start with. In fact, I don't, offhand, other than the squeeze theorem, I can't think of what else I would do. It's just, squeeze theorem is always what I would pawn this off on. But the trick to this problem is knowing how to bound your function so that it is between a smaller function and a larger function that approach the same values. Now, for these kind of problems that involve sine or cosine would have worked as well, because cosine is bounded between -1 and 1, too. So when you've got those expressions that contain sine or cosine, maybe the squeeze theorem might be something that'll work on that problem because you get that easy bounding just from trigonometry. Any question over what I've done? Now, I haven't proved any of these theorems. The squeeze theorem, we're not going to learn how it's proved. If you take an advanced calculus class, you'll go through the proof there. Right now, we just want to know how to use the tool. We'll worry about learning how to make the tool much later. Okay? All right, so I don't know how much use we're going to get out of this function called the greatest integer function, but at some point it's important that you see it because it does show up in various applications. But the greatest integer function, it's denoted by using these double-barred squared brackets. And by definition, it is the largest integer that is less than or equal to the number you're trying to take the greatest integer of. In short, it tells you to round the number down. I don't care what the decimal is, round it down. So 2.5, we would normally round 2.5 up. But the greatest integer says, look at all numbers that are less than 2.5 and take the largest integer that exists there. So in this case, the greatest integer of 2.5 is 2. For -2, if the number is already an integer, that's why it says less than or equal to x. So if you've got the greatest integer of a number that's already an integer, it's just equal to itself. -3/4, however, that's -0.75. You need to round that number down, so it goes down to -1. And the greatest integer of the square root of 50, well, what two whole numbers is the square root of 50 between? 7 and 8, right? Round the number down. So it's 7. That's exactly what this says. And the graph of this function, because it is a function, if I give you the value of x, there's no way you can give me two different greatest integers that are less than that number. So this is a function. And its graph looks like what you see in the bottom left-hand corner. It's what we call a step function. So for I wish I knew how to magnify or shrink an image. I don't know if this writing software has that capability. But if I just look at here, this is +1 and +2 right here. Every number that is between those two values is going to get rounded down to 1. So that's why this horizontal line exists right here at +1. Now, when you get to 2, it's going to instantly jump up to 2, and it's going to stay locked in at 2 until you get to 3, at which point it's going to jump up to 3 and just infinitely go in both directions. Now, there is also the mirror image of this function called the least integer function, which is just the opposite. It would be the smallest integer that is greater than or equal to your value. And that changes the steps a little bit. It moves them up 1 unit, and it changes what side the closed and the open circles are on. But did I fill that in? Okay. So if I were to look at these three limits, however, the limit as x approaches 2 from the left. So we're approaching 2 from the left-hand side. So you're approaching it through values of 2 that are less than 2. And if you're less than 2 but really close to it, what's going to happen is that greatest integer is going to round it down to 1. So on the left-hand side, this limit is coming in at +1. It's never changing. If you come at 2 from the other side, now you're coming at to 2 through values that are slightly larger than 2. And you're going to approach 2 as the right-hand limit. So when you approach whole numbers with the greatest integer function, that limit is not going to exist. But so long as you're between two whole numbers, like for example, if this limit instead of approaching 2 was approaching 2.5, well, 2.5 is right here. So as I approach it from both directions, I'm still on this same horizontal piece from both sides. So the limit would exist there. It just doesn't exist at the whole numbers themselves. Let's take that off. All right. Where does that put us? Okay. We're probably going to spend I'm not actually going to get to the formal definition of the limit yet, but I at least kind of want to talk about the motivation for what section 2.4 is going to talk about. If you go back to how we defined the limit in last week, we said that f of x, the limit as x approaches a of f of x is equal to L, if that f of x gets arbitrarily close to L as x gets sufficiently close to a. That was the wording we used to say that the limit as x approaches a of f of x was equal to some real number that we called L. Now, the problem is that those phrases, arbitrarily close and sufficiently close, that's not very precise. We need to nail down how close is sufficiently close. That's what we're going to talk about here. So if I look at this problem, so here's my function. I have, in this case, a piecewise function that is, its domain is all real numbers. But if I'm taking the limit as x approaches 3, remember, when you're taking the limit, you don't care, you don't care about what's happening at 3, just what happens as you're close to 3. So when I'm taking this limit, we're actually on that first piece of the graph because we're not equal to 3, but we're very close to it. So because I'm on that top piece of the graph, as far as this limit is concerned, that is the only piece of the graph that exists. And I could use direct substitution there and plug 3 in for x and get 2 times 3 minus 1. That's why I got this equal to 5. So this means, using the definition we used before, that we can make f of x arbitrarily close to 5 as we want by taking x sufficiently close to 3. Basically, you tell me how close I'm supposed to get to for f of x to get to 5, and I'll tell you how close x needs to be to 3 for that to always be true. So that's sort of what this next slide talks about. But rather than try to start this now, because when you see this definition, it's going to look a little cryptic at first, but I'm going to tell you 2 things. One, we're only going to be dealing with very basic limits that use this definition. We can make this harder by using a complicated function. We're not going to do that. We're going to be using this definition using very basic limits. Second, we're not going to use this definition all the time. We're going to use the limit laws for the most part. We're going to use direct substitution the most. But if the instructions at any point say, use the precise definition of a limit to prove something, you don't get to use direct substitution anymore. You don't get to use the limit laws. You must use this definition that we're about to define. And that's what we'll talk about today. Okay? All right, so let me stop this.